Last episode I promised you a number to beat. Today we actually go and get it. We are going to build a heatsink, a simple 5-fin block of aluminium, and simulate it properly in OpenFOAM from absolutely nothing to a real result. We'll make the geometry, we'll mesh it, and we'll solve the physics all together, the whole pipeline so to speak, from start to finish. Quick reminder of where we are. Episode 2, the baseline. This is phase 0. The reference design that every clever thing we do later gets measured against. And here's the design. 5 fins, each 2 mm thick, 20 mm tall, and on a 60 by 60 base. Air comes in at 3 meters per second, and the base is held at 350 Kelvin. Nothing fancy, and that's the point, is the honest starting line. Now the first thing most CFD tutorials do here is open a CAD program and draw the geometry by hand. We're not gonna do that. And the reason why is the single most important idea behind this series. We generate the geometry with this code. This is generate_heatsink_stl.py. It takes 3 numbers, number of fins, thickness, height, and it builds the heatsink for us as an STL file. Let me walk you through it. Up here, we define the base plate as a box. Then we loop over the number of fins, and for each one, we drop a thin box on top of the base, evenly spaced. And every surface gets turned into triangles because that's all an STL really is, a surface described by a mesh of little triangles. These are the main arguments that will be controlled by the code later. If you want to take a look at it, this will be available in the GitHub repository. So the way we run this script is we go to the script itself, and there is a help section that is provided with the script itself. As you can see, we can input a lot of things here. This length, width, base height. For us, these are fixed. What we want to control is the number of fins, the fin height, and the fin thickness. So let's just go ahead and add fins. Let's make 6 fins, and let's do 2 mm, let's do 5 mm. And it has created a solid named heatsink. Let's take a look at that. As we can see, this is the fin design. The essence of what we did here, we essentially added 6 fins, we added 2 mm thickness of the fins, and the fin height was around 5 mm. Let's just take a look at what this really looks like. So the fin thickness is indeed 2 mm. And the fin height itself is indeed 5 mm. And as we can see, the count itself, we do have 6 fins. So the script really works. So the whole object, base and fins becomes this shell of triangles. Feed it 3 numbers, get a heatsink. Change a number, get a completely different heatsink. No mouse, no clicking, no CAD. And I really want you to hold on to that because it's the hinge the whole series sort of swings on. We get to the optimizer in a few episodes and it's going to call this exact script hundreds of times with hundreds of different numbers completely automatically. None of that is going to be possible if a human is sitting and drawing it manually. Okay, we've got a shape, but OpenFOAM can't really solve anything on a shape, it needs a mesh. The whole space around the heatsink needs to be chopped up into huge number of tiny cells. So let's build one. 3 steps. Step 1, blockMesh. This just fills the entire domain, the wind tunnel around our heatsink, with a plain uniform grid of boxes. Think of it as the raw block of material we're going to carve the real mesh out of. As you can see, this is the block right here. Let's take a look at what the STL looks like inside it. If I just reduce the opacity, there we go. So this is the heatsink that sits inside this wind tunnel. On to step 2, surface feature extract. That finds the sharp edges of our STL so the mesher knows exactly where the geometry is. And step 3, the workhorse, snappyHexMesh. When I run snappyHexMesh, it takes that plain block of cells and carves it around the heatsink, snapping cells to the surface, refining them, making them denser and better near the fins where all the interesting physics happens. As we can see, this is the result. You can see the cells are sort of coarse here. At the bottom we can see the heatsink. Let's take a cut section and understand what this really looks like. Before that, let's just isolate the patch itself. And as you can see, this is the heatsink. The cells look quite coarse, but this will get the job done. We just want a good baseline. One honest note though, for this baseline and for hundreds of runs coming later, I'm keeping this mesh rather deliberately modest, not because I'm trying to cut corners, but because we're going to run this hundreds of times and extra cells cost extra real minutes. So we'll build a proper super fine mesh right at the end of the series where we actually validate the winner. But for now, this is good enough to compare designs fairly. Mesh done. Now, what are we actually solving? We're using a solver called buoyantSimpleFoam, and let's unpack that name because it sort of tells you everything. Simple means it's steady state. We are not simulating every second as it ticks by. We jump straight to the final settled answer, which is all we care about. Buoyant means it accounts for buoyancy. As the air near the fins heats up, it gets lighter and it rises. And to handle that cheaply, we use the Boysen's approximation, which is a fancy way of saying treat the air's density as constant everywhere except in the one term where gravity and temperature matter. It's a lovely little shortcut and it's accurate for the small temperature differences we've got. So in plain English, cool air gets pushed in by the fan, it flows over the hot fins, it heats up and carries that heat away. And buoyancy gives it a little extra nudge upward. That's the physics, start to finish. But a solver is only ever as good as the rules you give it at the edges of the domain. These are the boundary conditions, and honestly, getting them right is half the battle in CFD. So let's walk around the box. The inlet on the left, air enters at 3 meters per second at 300 Kelvin, room temperature. The heatsink surface itself, we pin it at 350 Kelvin. That's our heat source, a stand-in for a hot chip sitting underneath. The outlet on the right, we just let the flow leave, no reflections, no interference, and the top and sides, we make them slip. Frictionless, so they don't invent a fake boundary layer where there shouldn't be one. Put it all together and this is our little digital wind tunnel. Coming to the constant folder, we can see the gravity file. This will be useful for the buoyancy solver that we're going to use. Since we have heat transfer involved, we are not going to include any radiation model here as well. This right here is the thermophysical properties, which talks about how your fluid will behave when it encounters changes in temperature, as in how the density will vary, etc. As we can see, the mixture is the pure mixture in that we are only considering pure air. We are not going to consider the components of this air. The transport is also going to be constant. The thermo model that we are using assumes constant enthalpy, and the equation of state that we are using here, this is the Boysen-esque approximation, which only works for small temperature differences. And finally, the turbulence properties. We are not going to consider any turbulence here because the domain itself is not as complex. But if you want to include any turbulence effects, since this is flow over a particular body, I would suggest use K-epsilon model, but it's up to you. Ultimately, coming to the setup itself, the solver that we're using is the buoyantSimpleFoam, starting at 0, ending at 1000 iterations. Every 200 iterations, we'll just write the solution. We'll purge every final 3, but the 1 solutions here. One interesting thing to note here, we are writing a function for wall heat flux. What this will do is it will write wall heat flux as a field variable in the time folders. We can also take a look at the snappyHexMesh dictionary file. As we can see, we only have the cancellation and snapping set to true. We're importing the geometry, the STL, and we have a certain refinement box around the heatsink and the wake region to ensure that we have better coverage and better mesh cells around. For refinement surfaces, we're giving a maximum of level 2, and for refinement regions, we're just giving a refinement level of 1 here. Currently, we do not have any layering turned on. This will be turned on later when we perform the conjugate heat transfer analysis. Alright, geometry, mesh, physics, boundary conditions, everything is in line. Now let's run it. When I hit go, buoyantSimpleFoam starts iterating, and what you're watching scroll past here are the residuals, basically how much the answer is still changing with each step. At the start, they are high, the solver's still figuring things out, and as it converges, they drop and drop until the answer basically stops changing. That's how we know it's done. Now the fun part, let's actually look at it. Here's the temperature on the surface of the heatsink. Here's the slide through the middle so you can see how the heat spreads up the fins and out into the air. And this right here is wall heat flux. This is sort of the money shot. It is how much heat is leaving every part of the surface, add it all up, and we get our headline number. So, does it make sense? Because before you ever trust a CFD result, you do a gut check. OpenFOAM integrates that wall heat flux for us and tells us the heatsink is dumping about 24.6 watts. And that number isn't magic, it drops straight out of the physics. The surface sits 50 Kelvin hotter than the air, and Newton's law of cooling says the heat carried off each patch of surface is just that temperature gap times how well the moving air sweeps heat away. Add it up over the whole fin area, about 150 square centimeters, with an effective heat transfer coefficient around 30 from the 3 meters per second flow, and you land right on 24.5 watts, exactly what the solver computed. And here's why it has to balance. At steady state, nothing's heating up anymore. The metal's temperature is holding. If the heatsink isn't storing energy, then every watt going in at the base has to leave through the fins. It gets out in two steps: conduction, climbing up through the solid fins, then convection, peeling off their surface into the air. Energy in, energy out, the books balance, good. And there it is, our baseline 24.6 watts of heat, a Q over V of 1.08 watts per cubic centimeters, and a thermal resistance of about 2.0. That 1.08 is our line in the sand, the villain of the whole series. Here's the thing though, doing all of this once by hand took real effort. Setting up the case, meshing, solving, post-processing every single step, and in the next episode we're gonna need to do it not once but 15 different times. So picture doing everything you just watched by hand 15 times over. There's really no chance you can finish it quickly. So next time we hand the entire thing over to Python and watch CFD turn into a program that runs itself. This is my shameless plug again. Cool. If you're finding this useful, hit subscribe so you don't miss it. Again, the whole project's going on GitHub as we go. So I'll see you in the next one. Keep your residuals low.